HRW913P089. So the orbit of Earth about the Sun is almost circular, almost. The closest and farthest distances are this and this, respectively. So this is closest, this is farthest. Determine the corresponding variations in the following values. Okay. Hint, use conservation of energy and conservation of angular momentum. Alrighty, so they want the variations. Basically, they want the change from closest to furthest distance of these things. While the first one they want is total energy. Thing is, total energy is conserved, so there shouldn't be any variation in that. The answer is 0. Next, they want potential energy. Whoops, sorry. Don't know how loud that was. I just hit myself in the face. We actually have to do some math for this, but it's not too bad. Okay. In general, the potential energy of a two-body system is negative g, both masses, over the radius between them. Okay, so we just need to do this for both distances and subtract them, and then we'll find how much it changed. So let's do it for the closest distance first. I'm going to call that U close. I really should be calling it perihelion, though. Yeah, let's use the technical words. We have them. We should use them. Okay. So when something is the furthest it can get, we call that perihelion. So I'm going to call that UP. I'm also going to change pen size. Okay. So that's going to be G mass. Little mass is the mass of the Earth. We have to go look that up. I already did. Mass of the Earth is, I'm going to round that to 5.97 times 10 to the 24th. 5.97 times 10 to the 24th. Then we need the mass of the Sun, which I also have. Thank you, Google. That's 1.99 times 10 to the 30th. 1.99 times 10 to the 30th. And then at perihelion, that is when you're the closest, so that is going to be closest 1.47 times 10 to the 8th kilometers. So that's 1.47 times 10 to the 11th meters. Remember, everything's got to be in standard units. I really should be putting units everywhere. I just don't want to. Okay, G is 6.67 times 10 to the negative 11th. So put that all in your calculator, and we'll find the potential energy of the Earth-Sun system at perihelion is 5.3996. So that's 5.40. I don't know why I have trouble closing off my 5s. Weird. Times 10 to the 33rd joules. Oh yeah, and don't forget that that's a negative number. Okie dokie. Now I need to find it for aphelion, the furthest approach. Okay. Well, it's exactly the same except for the radius. In fact, I'm going to go ahead and store this last answer in my calculator, and then I'm going to do, last entry on my calculator and just go back and change this one number right here, 1.52, because heck, even this times 10 thing is the same. All I got to do is go back and change the 1.47 into a 1.52. So I'm going to go do that. And I get 5.22 times 10 to the 33rd. Okay. So now I just need to find out how much did it vary. So I just subtract these, and I've already got one of them in my calculator. It's actually the wrong one to get a positive number, but that's okay. Okay, let's see which one's. This one's bigger, so it should go this way. Okay. Put that in your calculator, and I already have mine in here, so I'm not even going to pause the video. Haha. Okay, and what I get is 1.78 times 10 to the 32 joules. which is exactly what they have for the answer over here. Good. Next up, they want the variation in kinetic energy. Well, here's the thing. Let's say when it goes from aphelion to perihelion, the potential energy decreases by this much. And that's the maximum decrease. Well, that's the decrease it has. Well, if the potential energy decreased by this much, because energy is conserved, the kinetic energy must have increased by this much. So the variation in kinetic energy should be exactly the same number, since whatever potential loses, kinetic gains, or vice versa. So you get the same answer for B and C. Just put it in. Next up, they want orbital speed. Orbital speed is a little bit harder. I'm going to show you a new way to do this. We haven't done this before, and why not do it now? Okay, while we're all on spring break. So let's look at the equation for kinetic energy. Just the equation. Here's the equation. So this is the kinetic energy of the Earth, basically, if this is the mass of the Earth right here. I can do this little thing where if I just took the derivative of both sides, okay, so the derivative of kinetic energy, well, there's just the 1 here, so it'd be like 1 dk. Okay, and then over here I've got, these are constants, so they stay. And then if I take the derivative of v, what I get is bring down the exponent, bloop, is a 2, keep the old variable, but bring the exponent down by 1, so that'd be v to the first or just v. And then to indicate what I was taking the derivative of, I put dv, where d of whatever I was doing derivative. Okay. Okay, that was probably very confusing. I'm going to rewrite this with simplifications. The 2's cancel here, so I end up with mv dv. Now, d is really an infinitesimal change, okay? But it's a change. So I can also approximate this symbol for change, okay? So I could say, instead of dk, I could say delta k. That's approximately mv, instead of dv, delta v. Now I'm doing this because I want to know the variation of speed, orbital speed. That's v. This is basically what I want right here. Delta v. Okay? So delta v is approximately change in kinetic over mv, where v is like the average velocity of the orbit. Okay. An average velocity of orbit is the distance it travels over the time it travels, which the distance it's traveled is the circumference of the orbit. Remember, if it's a circle, and it's almost circular, so that these are approximations. This is not going to be perfect. Okay? And then t, well, that's the time it takes to travel one orbit, which we call period. Okay? And we know the period of Earth. The period of Earth is a year, or actually, I looked it up to get it exactly right. There we go. It's 365.256 mean solar days. Okay? 365.26, say. Okay? You know what? Actually, let's use the whole thing. 2564. Okay? Days times 24 hours per day times 3,600 seconds in an hour gives me a period of, calculator, 3.16 times 10 to the 7th seconds. Okay, so that's going to go in here. I have the radius. So if I put all this in here, what I get is that the variation in velocity should be the variation in k over m times, now this v is on the bottom, and v equals all of this, so that's the same as multiplying by the reciprocal of all of this. So what I get is t on top with 2 pi and r on the bottom. Okay, which all of these I know. All of these I have a number for. Keep in mind for r, in the problem itself, they gave us the radius at aphelion and perihelion. We're going to use the average radius, which is right here, 150 million kilometers. Okay, so keeping in mind that r equals 150 million kilometers, that would be 10 to the 6th kilometers, or 150 times 10 to the 9th meters. I know that that's not in proper scientific notation, but that's how it was written. And we're just going to put it in the calculator like that, it'll be fine. So if I put in for delta K, our answer for C, where is that? There it is. If we put in our answer for C, for change of kinetic energy, this is the period. Mass of the Earth, I still have, there it is. Yay, Google. And 2 and pi, you know. And then r is this. If you put all that in the calculator, we get, I get 990 meters per second. However, the answer wants our answer in kilometers per second, so I've got to divide by 1,000 to get it into kilometers, which is 0.99 kilometers per second, which is the answer that they got.